All right, today we're taking a look at section 3.3. We're talking about increasing and decreasing functions and the first derivative test. All right, so to start with, the first two descriptions are things that you intuitively know. You know what it means for something to be increasing, and you know what it means for something to be decreasing, but these are formal definitions. So if the x value comes before the y, or before, I didn't say that right, x1 comes before x2 on the x-axis, and it's increasing, then it means that f of x1 is less than f of x2. And likewise, if it's the other way around, that f of x1 is greater than f of x2, then that means it's decreasing. And I'd like to draw a sketch of what that looks like so that you can see that it's exactly what you know it to be, it's just formalized. So just like we read English, we read our graphs from left to right. So here's x1 and x2. So that's the first description. It says x1 is less than x2. And it's saying that the values here, if the f of x value, f of x1, is less than f of x2, then the graph is increasing. And we all said, well, yes, of course. I read the graph left to right. I see that that graph is going uphill. It's increasing, right? And we can draw almost the same picture, but turned around, reflected, for the decreasing. So I have x1 and I have x2. But now the f of x1 value is higher. It's larger than the f of x2 value. And that one would be decreasing. It's going downhill from left to right. All right, so let's take a look at a theorem that talks about these ideas of increasing and decreasing. So we're going to suppose that f is continuous, so no holes, no gaps, nothing like that on the interval. And the derivative is positive. Okay, you take the derivative, and it's always a positive value on a particular interval, a particular set of values, maybe the whole graph, but a particular set of values. If that happens, then the graph is increasing on that interval. And if the derivative is negative, then the graph is decreasing. And if you have a portion of the graph, or even just a single point potentially, where the derivative is equal to 0, it would be constant on that interval. Okay, these are all things that if we sort of change our language around, you're going to be like, oh yeah, of course. Remember, derivative just means slope, right? So what does it mean for your slope to be positive? Well, it means that, right? So obviously, if the slope is positive, it's an increasing graph. And if our slope is negative, it's a decreasing graph. And if our slope is 0, that's not very good, but that's not too bad. If our slope is 0, it is a constant graph. So anytime you're looking at this and you're like, oh man, there's so much notation, try and interpret the notation in language that helps you to understand it better. Derivative means slope, right? It means the slope. What's the slope doing? Well, if the slope is positive, then it would be increasing. The graph would be increasing and so forth. And this relates to the first derivative test. So the first derivative test talks about how can we actually decide where graphs are, in fact, increasing and decreasing. Well, the previous slide says that we can do it based on what the derivatives are doing. So what we're going to do is we're going to suppose that we have a critical number between a and b. So we've got an interval a, b. And a critical number, if you'll remember from our last material before break, is a place where the derivative is equal to 0 or doesn't exist. Okay? Doesn't exist, maybe it's got a sharp turn, or it's equal to 0, it's got a peak or a valley. All right? So those places are critical numbers. And if we have a derivative, i.e. a slope, changing from positive to negative, or changing from negative to positive, this will indicate for us that the graph is changing from increasing to decreasing, or decreasing to increasing. And you'll notice that if it goes from increasing to decreasing, what do you suppose is happening right here? It's a peak, it's a maximum, right? And if the graph goes from decreasing to increasing, we've got a minimum. And as we do these, there's a lot of ways that you can look at how to think about this. One is very definitional, to go back and think through this definition every time, and that's okay. I am a graphic person. I see visually really, really well. There was a program that I was involved in when I was a teenager in our denomination called Teen Bible Quizzing, and I memorized massive amounts of scripture, and I could see it on the page. That's how my brain works. So I'm going to focus a lot on visual interpretations of these because that's how I think. And if that doesn't work for you and you want to come chat with me and we can find a different way that works better, that's totally cool. All right? I know that we're not all visual people. I get that. The last one, part C, says, if it has the same sign, then it's simply not a local extrema. And I'm going to show you an example of one, just a super tiny sketch because I don't have much space. But if the graph were to do something like this, and of course I've made it very dramatic looking, this point right here certainly seems like if I drew a tangent line, it would be horizontal, right? But the graph is increasing beforehand and it's increasing afterwards, so it's not a maximum minimum. And that can happen. And this equation actually is one that you're quite familiar with. It's y equal x cubed. The y equal x cubed graph has this happen. So that will happen occasionally, and we need to expect that that might be the case sometimes. It's not always a max or min. All right, so we need to practice how this works with some examples. And I've tried to do, like always, some examples where we've got polynomial stuff and rational stuff going on, and others where we have some trig. This directions say, identify the open intervals on which the function is increasing or decreasing. So this particular question doesn't ask about maxes and mins. It just asks about the increasing and decreasing nature of the graph. Either question, whether it asks about maxes and mins or asks about increasing or decreasing, has the same steps involved. It just has a different type of answer at the end. So when we're looking for these, we're always going to take derivatives, set them equal to 0, and solve. All right, so if you want to sort of make a note to yourself that the first thing we're always going to do here is we're going to take the derivative, set it equal to 0, and solve. So go ahead and do that for this function. Find the derivative, in this case, of y. And if you're struggling a little bit with the second part, remember this is 4x to the negative 1, right? All right, so what is the derivative of x? 1. How about 4x to the negative 1? Good, negative 4x to the negative 2. Everybody good with that? Okay. You can leave it written like that if you'd like. I kind of don't like negative exponents personally. They look a little bit harder than they really are to deal with. So I would prefer to rewrite it that way myself. And what we want to do is we want to set it equal to 0, right? In fact, I'll do it over here so I have more space. There's several things you could do to solve this. You could get a common denominator. That's totally fine. You could do that. A lot of times it's easier to get rid of the denominators completely than to actually get the common denominator and work at it from that perspective. So I'm going to do it from that way, but if you want to do common denominators, it's totally fine. You would get a common denominator by not a common denominator, but you would get rid of the denominators by multiplying by x squared on both sides. So I have x squared minus 4 on the left, and I have still 0 on the right. And x squared minus 4 is an easier function to solve for than 1 minus 4 over x squared. So whether you decide to factor this, which you can, or whether you decide to move the 4 to the right and take a square root, which you can, either way, you're going to get that x is equal to positive and negative 2. So most of ours are going to be factored form, so I'll go ahead and do this one as though it's in factored form as well. X minus 2x plus 2, so x is equal to 2 and negative 2. Now there is one more place where it could change from increasing to decreasing or decreasing to increasing, and that's when the derivative doesn't exist. So where would this derivative, look at the original one before I started manipulating things with the setting it equal to 0. This form I find the easiest one to look at. Where would this derivative not exist? At 0, right? I can't let x equal to 0 because that would be a denominator to 0. So that is an additional critical point. Okay, so this is where the derivative does not exist. That's where that's coming from if you're sort of thinking about that. But I have 3 critical points here. Okay? So here's what we're going to do. This is where that visual stuff I was telling you comes into play for me. We're going to set up a number line. And on the number line, we're going to mark these 3 places in order. So I'm going to do negative 2, 0, and 2. And what I want to do is I want to test values between those points. And it doesn't matter what you test. So make it easy, make it hard, make it whatever you want. But it doesn't even have to be what anybody else tests. So if I test, for instance, maybe I test the number, that's not good. I need a different color. We'll try it. If I test the number negative 3 over here and you test the number negative 4 over here, we're going to get the same thing. And I don't mean we're going to get the same thing by the same number, because we probably won't get the same number, but I don't really care about numbers. What I'm going to care about is what the sign is. So let's actually just decide, so that we can all do it together, what numbers to check in these intervals. So I'm going to choose negative 3 that comes before negative 2. What number would you like to pick between negative 2 and 0? Negative 1 would be great. How about between 0 and 2? 1? And after 2? Fabulous. Okay, so these are our 4 test points. All right, the 4 locations we're going to test. Okay, so let's come back up to my sort of list of the things that I'm doing. After I set things equal to 0 and solve, what I do, and for me, visually works, is to create a number line. And test points. And then I'm going to actually test the points. So this is really important because people tend to get to here and then they sometimes forget where they test the points. So we're going to test the points in f prime, not in f. I don't care what the function's doing. I care what the derivative's doing right now. Okay, what is the derivative doing? Is the derivative positive? Is the derivative negative? So we're going to test f prime of negative 3. F prime of negative 1, F prime of 1, and F prime of 3. And what I want to know as I test them is what sign do I get out of the function. So my function, actually let me write it up here above these, in sort of pretty-ish form for F prime, was 1 minus 4 over x squared, right? Feel free to put it in your calculator if you wish. You can actually do that in the table. You're going to test 4 points anyway, so if you want to put them in the table, you could do that. You would put in the calculator 1 minus 4 over x squared, and then in the table you can plug in negative 3, negative 1, 1, 3. Works real fast. And what we already know is what is the sign. Do I get a positive or do I get a negative? So what happens on this one if I plug in negative 3? Do I get a positive or do I get a negative? It's a positive, that's right. I get a positive. What if I plug in negative 1? It's a negative, actually, on that one. Yeah, it's negative. How about if I plug in 1? Also a negative. And 3? Positive. So I want to go back to my number line, and I want to put those positives and negatives on there just as a reminder to us. Because what they mean is are they increasing or are they decreasing? Positive means it's increasing. Negative means it's decreasing. So this is sort of the visual that's going on. Uphill or downhill, uphill or downhill. Positive, it goes up. Negative, it goes down. And from that picture, we can answer the question about increasing and decreasing. And the intervals on which it's increasing and decreasing are these intervals that I'm getting along my x-axis here, right? There are 4 intervals, and I need to recognize that there are 4 distinctly different intervals. They're all doing something specific. So on the first interval, it's negative infinity to negative 2, not negative 3. I tested negative 3, but the interval went to negative 2. I have an interval from negative 2 to 0, an interval from 0 to 2, and an interval from 2 to infinity. So what is happening from negative infinity to 2? Negative 2, sorry. It's increasing, right? How about from negative 2 to 0? It's decreasing. 0 to 2, decreasing. And 2 to infinity, increasing. Now, if you're doing work that you're writing down, you can leave it written like that. I have a feeling that WebAssign is going to want you to sort of attach all the pieces that are increasing into one line, and then all the pieces that are decreasing potentially into one line. So what you could do if it needs you to do that is you could actually put these together like this with that U in between. And the same thing for the other one. These pieces were both decreasing. You can put this together with a union in between. And I've heard mixed reports back about whether WebAssign cares whether the union symbol's there or not. So maybe it cares, maybe it doesn't. Jared.
For the decreasing, would you need the union if it's like it's decreasing between the
Yeah, that's a good question, and you do. And the reason that you need the sort of the breaking point of 0 is because at 0 the derivative doesn't exist. And so you want to make sure you're excluding the fact that that's not decreasing at 0. Yeah. All right, ready to try a trig one? I know you are. You all love trig, don't you? I know. Same directions, okay? This one is cosine squared minus cosine. It does have an interval on which to look to begin with, 0 to 2 pi. That happens a lot with our trig functions because otherwise you've somehow got to write descriptions down for all intervals and it becomes cumbersome and awkward. So we do have an interval on which to only consider our values to begin with. Directions are still the same. Okay, so over here, I wrote down that we were going to take f prime of x and solve it, create this number line and find some test points, and then actually test the points, right? And when we tested those points, we have to interpret what's going on. So the first direction is the same here. I need to take the derivative. And this is one that's similar to what you did on the test when I asked you to find the second derivative because it's got a cosine squared. So what this actually means, remember, is that you've got the cosine of x, and it is squared. That's what that means. So we're going to take the square down to the front. We're going to rewrite the cosine of x. And if it helps you to think about it, you've got it to the power of 1 now. And then the derivative of cosine is negative sine. Okay? On the second piece, you just have minus cosine. So the derivative of cosine's negative sine means I have plus sine x at the end. Okay? I can clean this up just a tiny bit maybe. I've got negative 2 cosine x sine x plus sine x. Not too much to clean up, but a little bit. And I'm supposed to take this derivative and set it equal to 0. Okay, so with trig functions, it's a little different than over here. Over here I said a lot of times it breaks down into this idea of being able to factor. And the reality is that this does too. You just don't always think about it that way. But if there are pieces that match, we can factor this. And in fact, both of the trig pieces that we have a sign in them, right? So we're going to factor out sine of x. And if I do, that leaves me with negative 2 cosine of x plus 1. And then again, just like with polynomials, I take each factor and I set them equal to 0 to solve. So I have sine of x equals 0, and I have negative 2 cosine of x plus 1 equals 0. All right, the first one is easier. Do you remember where sine equals 0? Between 0 and 2 pi. 0, what was it? Pi and 2 pi. And 0 and 2 pi are actually my interval endpoints that are not included, right? Do you see that up here? So the only point that's actually going to come out of this one between 0 and 0 and 2 pi is pi. One possible value from this particular factor. But negative 2 cosine plus 1 equals 0, that actually requires you to remember some trig values from a unit circle kind of stuff. So if I solve this, I have negative 2 cosine of x equals negative 1, and I have cosine of x equals 1/2, right? All right. I told you at one point you were welcome to have a unit circle as you sort of refreshed your mind, so maybe some of you still have that with you or remember it better now than earlier on. Where do the cosine values actually equal 1/2? Very good. It is. It's pi over 3 and 5 pi over 3. That's it. The values anyway between 0 and 2 pi. Yeah. So there are 3 values here that are my critical numbers to test between. So on this one, when I create my interval, it isn't sort of an open-ended interval. It really does, it starts at 0 and it ends in 2 pi. So as I'm looking for numbers to test, I definitely have to be aware of that. And I need to choose the numbers so that they're in between each other. So of pi over 3, and 5 pi over 3, which one comes first? Pi over 3. And then pi. And then lastly would be 5 pi over 3. Okay, so as we're doing this, sorry, I'm running out of space, so I'm going to shift this over a little bit. We need the testing values between these values, right? And while it's true that you could sort of be focusing on, well, what trig value, what pi value is between 0 and pi over 3, and you could use that, like you could use pi over 4. That'd be okay. You could also use other numerical values. For example, between 0 and pi over 3 is the number 1, because pi is about 3, right? A little bit more. So pi over 3 is a little bit more than 1. So the number 1 is between 0 and pi over 3. So you could use whole number values, you can use decimal values, you can use pi values. It doesn't matter, but you do need to pick some values in these intervals to test. So how about you guys tell me what you would like to test between 0 and pi over 3? 1. How about between pi over 3 and pi? 2 is a good one. Pi and 5 pi over 3?
4.
And 5 pi over 3 and 2 pi? You know what, Emma, those are all the values that I have written down exactly. It's like you're reading my notes. I kind of like the whole number of values when I can use them. They're easier to input. And where do we test these values? In what function? The derivative. We're testing them into the derivative, right? My notes are over here on the top here. We put the test points into f prime. So in your calculator, if you would like, so that you don't have to enter it all by hand, you can enter the derivative, which is this piece right here. Negative 2 cosine x sine x plus sine x. So you're going to test f prime of 1, f prime of 2, f prime of 4, and f prime of 6. And remember, all we really care about is what? The sign. Is it positive or is it negative? Okay, so plug those in. Figure out if you've got positives or negatives. And then we'll fill in our number line. What happened at 1?
Negative.
It's negative. At 2?
Positive.
And at 4?
Negative.
And at 6?
Positive.
Yep. Lots of positives and negative changes going on. So negative, positive on my number line. And negative means downhill. Positive means uphill. So it looks something like that. So let's actually put it together the way we ended with it on the last one, where we identified where it was increasing and where it was decreasing in an interval form. So where does this graph begin increasing? Pi over 3. And where will it end increasing? At pi. And then it picks up increasing again at 5 pi over 3, and it ends at 2 pi. And then for decreasing, I have the other pieces, right? From 0 to pi over 3, and from pi to 5 pi over 3. Yeah, I got that right. Okay, all good? Yeah.
Will we put brackets on the end of the 2 pi if it's 0?
It's a good question. I almost said something and I was like, I'm going to wait and see if anybody asks because I don't want to confuse the issue if nobody notices or thinks about it. There's 2 answers to that. Okay, so the answer specifically for this question is no, because the intervals themselves was given up here. They didn't include them.
Oh.
Did you notice that? So on this one, it doesn't include them anyway. The answer sort of in general is if you take a look back at how we've described them, all of our intervals for where increasing and decreasing are always described as open intervals. So even if these 0 and the 2 pi were included, with increasing and decreasing, we always describe them in an open interval sense. And I say that because that's how your book and how I was always taught to look at this. The college algebra book that we use on campus does not teach it that way, which is super unfortunate. So yeah, it does it weird. But yeah, so open intervals for increasing and decreasing. Okay, let's take a look at the next set of questions. These directions are changed a little bit. They want us to find the critical numbers, but we've been doing that anyway, right? The critical numbers are where the derivative is equal to 0. Part B says to find the open intervals in which the function is increasing or decreasing. We've been doing that. That was the last set that we did too. C is the part that's different, to apply the first derivative test to identify relative extrema. So if I were using that same set of directions on this problem, I would have done everything that I did except that at the end, I would look back at my graph and I would say, hey, look, right here, it goes from decreasing to increasing, so where they meet must be a minimum, right? And over here, it went from increasing to decreasing, so up here where they met was a maximum. And that's the only part of this, part C, that they're asking you to look at. They're asking you to make that claim based on the first derivative test, and that's what the first derivative test says. The last part, part D, using a graphing utility to confirm your results, basically is saying, hey, why don't you graph it and just make sure that you're right? That's all it is, okay? So graphing utility is just confirming that what you have found makes sense. So on this one, we've got a very basic function because I didn't want us to get hung up in a lot of the details on the first one. So we're going to do the same steps we did before, set it equal to, take the derivative, set it equal to 0, and solve. So what's the derivative of this polynomial? Negative 4x plus 4. And where will this equal 0? At x equal 1. Super simple on this one, right? And you know what the shape of this graph is, right? I hope you do. We're about to find out in a minute. All right. So this would be sort of part A. Part A actually said find critical numbers. Well, that's what I just did. I found the critical numbers. There's only one of them. It's at 1. Part B is to do what we were doing on the last one next, which was, or last problems, which was to set up a number line and actually figure out where it's increasing and decreasing. So we need to test a number before 1 and after 1. What number do you want to test before 1? 0, and after 1? 2. All right, so these are our test points. And where do we test our points? In what function?
In the derivative.
In the derivative, always in the derivative. So we would take f prime of 0 and f prime of 2. I wouldn't even bother to put this in a calculator because the function's derivative is a very straightforward one, right? It's negative 4x plus 4. So if I plug in 0, do I get a positive or negative? Positive. And if I plug in 2, do I get a positive or negative? Negative. So this is positive, this is negative. Positive means up, negative means down. All right, so there's all the rest of the information I need right there on that little picture. The answer to part B now is about the increasing and decreasing. So where is this graph increasing? Where?
Negative 0.
Okay, so it's increasing over here, right? So negative infinity is the farthest left because this one did not have an interval like over on this one, right? This one had an interval where it started at 0, stopped at 2 pi. I don't have that on this function. So this is negative infinity up and until 1. And then it would be decreasing on the other half, which is from 1 to infinity. Good? So part C says, using that information, tell me if you have a max or min. So what do we have? Do we have a max or do we have a min? I have a max, right? This point right here is a peak of what's going on. It's a maximum. Now, it does say find all relative extreme. It just says relative extreme in here. Oopsie, I didn't mean to mark that out. I meant to highlight it. So it's got a maximum at x equals 1. If it asked you to find out if it was, if it asked you to find the point, like an xy ordered pair, we would take that value 1 and we would plug it back in to our function. And if we do plug this one in, we actually get 5. So I'm just trying to cover bases. If WebAssign asks you what point do you have a maximum or minimum, the point would be at 1, 5. Does that make sense? Jared?
When I did this in high school, when
Yeah.
we answered it on the exams, we had to do like, there's a maximum at this point because you're going to want to.
Yeah, so if you're showing your work in a graph, then the work's there. I think that WebAssign is going to ask you for an ordered pair. I think that's how they do it. I'm getting some nods. So I think that it's going to ask it as an ordered pair, but I know what you're talking about. I don't remember if our book focuses on that or not. The directions on this particular problem are very vague. Like, that's why I'm looking, I'm going to, they want you to actually have a point. It just says apply the test to identify. And so, yeah.
Like, I can figure out what kind of question, like what kind of answer they want from the website, but like just your preference, like you want us to say like.
I'll be really clear.
Okay.
Yeah, I would say on it, like, find the maximum or point or something like that. I'd use the word point, or I would say X value.
I just know like some people, like some professors and teachers are a little bit picky about what the answer is.
Yes.
What you answer it.
Yes, I will be real clear about what I want you to do when I write it as a question on something, so, yeah. All right, D says to confirm it with a graph. I know you guys know what this graph looks like. Roughly speaking, it looks like this, right? Yeah, and if you graphed it with a calculator because you had something that you weren't familiar with, you could confirm, in fact, that it does, in fact, have a maximum point. It's a parabola. It's going from increasing to decreasing, and it would be sketched on the graph. This is actually where it comes. It's about like this. It looks roughly there. Okay, and you could confirm that, yes, everything I just found makes sense. Okay, let's try another one. I may have to post the last one as a video attachment, but let me do number 4 with you at least. We can do that one. Critical numbers, intervals, extrema, all the same directions. So we're starting with a derivative. So what is the derivative of x to the 1/3? Right, 1/3 x to the negative 2/3. And the derivative, of course, of the plus 1 is 0. If you would like to rewrite this so that it's easier to sort of look at, this is 1/3 x to the 2/3, or you could put cube root of x squared, if you like that better, like this. If I'm setting this equal to 0, it can't. This can't equal 0. If you think about, like, what would I do? How would I solve that? Well, one way you might think to solve it is to cross multiply. But if you cross multiply, do you see what's going to happen? X's are going to go away. There's not going to be a variable left in the function. And the reason that's happening, and the reality of what's really going on, is that in order for a fraction to equal 0, the numerator has to equal 0. And this doesn't have a numerator that's able to equal 0. The numerator is 1. I can't get this to equal 0. So this flat out doesn't happen. But it does have a place where it doesn't exist. Where does this function not exist? At x equals 0. So at x equal to 0, the derivative doesn't exist. So I do have a critical point, because remember, critical points are where the derivative is equal to 0 or where it doesn't exist. And this doesn't exist at the point 0. So that is part A, my critical numbers. Part B is my number line. Here's 0, and we'll test numbers before and after. I'm a fan of -1 and +1, so we're going to go with those. And we're going to find where the derivative is equal. I'm sorry, not where the derivative is equal. Where the derivative, what the derivative is at -1 and what the derivative is at +1. So if I put in -1 into this equation here, -1, I square it, I take a cube root and multiply it by 2, and then 1 divided by that. Do I get a positive or a negative? It's a positive. And how about if I plug in the number 1? Also a positive. We haven't had that happen yet. Positive, positive, which means it's doing what? It's increasing on both of those pieces. So as I'm interpreting what I have found, this is increasing from -infinity to 0 and from 0 to infinity. It's not decreasing anywhere. Don't have to write it down because it doesn't apply. And on part C, where it asks me about relative extrema, maxes and mins, what am I going to say? Yeah, there are no relative extreme values. And if you confirm this with your calculator, it looks like this. Kind of like an x-cubed graph. Not exactly, but kind of like an x-cubed graph. You can see, if it were flat enough in the middle, mine's not looking very flat, but it flattens out in the middle. It doesn't flatten out in the middle. I said that wrong. It becomes vertical in the middle is what I meant to say. I get a vertical tangent line, and a vertical tangent line has an undefined slope. We talked about that they don't happen very often, but occasionally we see it happen. This is one of those cases. So the slope doesn't exist in the middle, but on either side of that, it is an increasing graph. All right, let's at least start what happens on problem 5. Same directions, we're going to take a derivative. So, actually, I think I've been writing all my letters down differently, didn't I? That's okay. What's my derivative of x plus 2 sine x? 1 plus 2 cosine x, and it does limit my interval. I'm noticing that at the beginning there. That part was the part that's different. Because I'm working with a trig function again, it's telling me to go between 0 and 2 pi. All right, cool. So I'm going to set this one out equal to 0. Looks very familiar. We've done this one already today, right? Or at least almost done this one. This one would give me that the cosine of x is -1/2. Not positive, but negative this time. And between 0 and 2 pi, that's my interval, where does my cosine value equal -1/2?
No, not negative, sorry.
It's okay.
Pi over 3, and then
All right, 2 pi over 3 and 4 pi over 3. And we can set up an interval, right? Okay, I am trapped still between 0 and 2 pi because I'm working on this particular trig one. 2 pi over 3 is smaller than 4 pi over 3. And I'm testing values in between. So what number would you like to test before 2 pi over 3?
2.
2?
Yeah.
Okay, how about between 2 pi over 3 and 4 pi over 3?
Let's do 3.
And between 4 pi over 3 and 2 pi?
5.
Okay, is everybody good with those numbers? Okay. Into what function do I test them? The derivative function, right? So I'm going to find f prime of 2, f prime of 3, and f prime of 5. And this is my derivative function right here. What happens at f prime of 2? Positive? 3? And 5? Positive. So positive, negative, positive. Positives increasing, negatives decreasing. That's supposed to be a positive at the end. Positives increasing. Do you see my maxes and mins? They occur again on this one, right? So on this one, it says, where is it increasing? Decreasing. We've already done several of those, so let me just skip to the point where it talks about the relative extrema. Okay, so the relative extrema is that it has a maximum. Where? Where is the maximum on this particular picture going on? What x value? At which one? At 2 pi over 3. Right here I have a maximum. So I have a maximum at 2 pi over 3. And I have a minimum at x equals 4 pi over 3. And if it specifically asks for you to find the ordered pairs, like the xy ordered pairs, we would plug that back in where? The original function. The original function tells us where on the actual graph that those things are happening. All right, so yes, I realize that we didn't quite write down all the details. We would graph this to confirm it with our calculator, and of course write down the details about the increasing and decreasing. Okay? All right.